At 9:13 on the night of December 2nd, 1959, a sound like a cannon shot echoed through the gorge above Frejus. Within seconds, 50 million cubic meters of water, enough to fill 20,000 Olympic swimming pools, tore through a valley where 400 people were sleeping. The dam that held it back was the thinnest arch dam of its height ever built. It had stood for 5 years. It failed because of a science that did not yet exist. The Malpasset Dam was a prestige project for post-war France. The Var département needed irrigation and drinking water for the Côte d'Azur, and engineer Coyne, the most celebrated dam designer of his generation, proposed something audacious. An arch dam, 66 meters high, but only 6.78 meters thick at the base, thinner than most apartment buildings are wide. Coyne's design transferred the reservoir's force laterally into the canyon walls, the way a stone arch over a doorway pushes weight sideways into the frame. It was structurally elegant. It was also structurally unforgiving. Every kilonewton of force had to go somewhere, and that somewhere was the rock. Here's the problem. Nobody checked the rock. The geological survey of the Gneiss Foundation, the bedrock the entire dam leaned on, was never funded. The budget had room for concrete. It did not have room for geology. To understand why this mattered, you need to understand how an arch dam works. A gravity dam, the big, heavy kind, resists water by sheer mass. It sits there and says, "I'm heavier than you." An arch dam does something cleverer. It curves upstream, so the water's pressure actually compresses the arch, and the arch transfers that compression into the canyon walls on either side. Less concrete, more physics. But physics has a condition. The canyon walls have to be solid. If the rock shifts, even slightly, the arch loses its compression path, and the elegant transfer of force becomes a catastrophic concentration of stress. Coyne had built dozens of arch dams. He understood the theory better than anyone alive. What he couldn't account for was a flaw in the foundation that no instrument of his era could detect, because the field of study that would have detected it hadn't been invented yet. After the collapse, investigators found something in the gneiss bedrock that explained everything. A tectonic fault ran perpendicular to the river, just downstream of the left abutment, the point where the dam's arch pressed hardest into the canyon wall. The gneiss was nearly impermeable. Under normal conditions, that's a good thing. It means water doesn't seep through. But when the reservoir filled, water found the fault. It seeped into the gap between rock layers and had nowhere to drain. The pressure built underneath the foundation. Slowly, invisibly, like air inflating a tire beneath a parked car. Except the car was a 66-meter dam holding back a lake. This failure mode, hydrostatic uplift beneath an impermeable foundation, would later become a textbook case in a discipline called rock mechanics. In 1959, that textbook didn't exist. The discipline didn't exist. The engineers weren't negligent in the way we usually mean the word. They were working in a domain that literally had no name. November 1959, 50 centimeters of rain in 2 weeks. Cracking sounds from the structure. A trickle of clear water appearing high on the right dam face. Clear, meaning it wasn't runoff. It was coming through the rock. By noon on December 2nd, the reservoir was at absolute capacity for the first time in 5 years. 13 centimeters of rain had fallen in the final 24 hours alone. Dam guardian Frejus saw what was happening. At noon, he urgently requested permission to open the discharge valves and lower the water level. Permission was denied. Bureaucratic channels, authorization protocols. The valves didn't open until 6 p.m. In 3 hours of discharge, the water level dropped by centimeters. The dam needed relief in meters. It got centimeters, and the uplift pressure beneath the left abutment kept building. At 9:13 p.m., the uplift pressure reached a critical threshold. The left abutment thrust block shifted. A crack propagated across the full 222-meter arc of the dam. The structure that had taken 2 years to build came apart in seconds. 50 million cubic meters of water entered the gorge as a wall 40 meters high, traveling at 70 kilometers per hour, carrying concrete monoliths weighing up to 600 tons. The villages of Malpasset and Bozon were obliterated. A highway construction camp, workers asleep in temporary barracks, was swept away without warning. 21 minutes later, the wave reached Frejus, still 3 meters high. No evacuation had been ordered. Flooded roads blocked emergency vehicles. 423 people died. 135 of them were children. 79 children were orphaned. 155 buildings were destroyed. The criminal trial spread blame across every party. Coyne's firm, the Département du Var, the contractor. The court found the bureaucratic delay of the discharge order indefensible. But the deeper verdict was epistemological. The design was not wrong, it was placed on the wrong rock. And the 1952 budget that had room for concrete, but not geology, ensured that no one would know until the reservoir filled for the last time. An entire category of knowledge was missing. The interaction between water pressure, impermeable rock, and structural foundations, what we now call rock mechanics, was not a recognized field of study. The disaster changed that. In 1962, the International Society for Rock Mechanics was founded, directly catalyzed by Malpasset. Dam safety legislation was overhauled in France and adopted internationally. Every major dam built since requires the geological survey that Malpasset's budget cut. The dam that broke because of an unknown science created that science. The fractured arches of Malpasset still stand in the gorge north of Frejus, France's most visitable engineering disaster site. You can walk up to them, touch the concrete, and the lesson they teach isn't about dams, it's about the dangers of building anything. A bridge, a system, a policy, on a foundation you assumed was solid but never actually tested. The most dangerous faults are the ones you don't have a name for yet.